Hello, welcome to the Bakwas channel for self-paced tutorials on Internet of Things. This video examines the Arduino UNO R4 Wi-Fi microcontroller board which was introduced last year in March 2023. I avoided examining the UNO R4 intentionally when it was announced in March 2023. I was working on the Arduino Giga at that time. The Giga was considerably more feature-rich. Of course, at what price point, you may ask? I will concede that point. At that time, I felt that UNO R4 would be a retrograde mistake. However, recently I was evaluating a critter camera to detect foxes in the backyard. I needed a cheaper board than the Arduino Giga. I evaluated the proof of concept using the ESP8266 board. On a side note, I will publish some videos on that project soon. However, given the struggles in securing multiple analog ports on an ESP8266 board, I decided to evaluate the UNO R4. I must confess that I am fairly impressed with the new features of this board. The UNO R4 board is available in two models, the Minima and the Wi-Fi. This video presentation covers some of the basic demonstrations with the UNO R4 Wi-Fi using the code examples published by Arduino. Only the newer features of the UNO family will be examined in this video. You will not become an expert on Arduino UNO R4 at the end of this presentation. To achieve that goal, you will have to practice, and practice, as the saying goes. Most importantly, please correct any mistakes that I may have made in this tutorial owing to my personal handicaps, because thanks to your feedback, I can only improve myself. The key differences between the two boards are: the Wi-Fi board has Wi-Fi and Bluetooth support. The Minima does not have these wireless options. The Minima does not have a 12x8 LED matrix. The Minima does not have a Qwiic connector interface. Every other specification is common to both boards. Both boards have a real-time clock support and capacitive touch sensing unit. Power to the board relies on Schottky diodes for overvoltage and reverse polarity protection. There is a barrel jack connected to the voltage in VIN pin. The recommended input voltage is from 6 to 24 volts DC. In keeping with the times, power to the board is at 5 volts DC, as well as the desktop connection is through the USB connection. Here is the pin-out diagram of the UNO R4 board. This slide is not meant to be an eye test for you. The image is published by Arduino at their website as a PDF document. I am sure that if you work on the UNO R4 board, you will download a copy for your own use. The pin layout is meant to be backwards compatible in all respects but one. The desktop interface cable now uses an USB-C connection on the board. Other than that, all previous projects can connect with the same positions on this new board without change. Of course, there are a few new terminal points, such as the Qwiic interface and the role of the VRTC pin to support the onboard real-time clock. One distinction that should be noted is that the microcontrollers and the general purpose input-output GPIO pins on the UNO boards operate at 5 volts DC. The ESP32 chip for the Wi-Fi Bluetooth functions uses 3.3 volts DC. The board supports input voltage in the range from 6 to 24 volts. The microcontroller is the Renesas RA4M1 Arm Cortex-M4 chip. The clock runs at 48 MHz. The static RAM capacity is 32 kilobytes and the flash RAM is 256 kilobytes. It supports a digital to analog converter, a real-time clock, and the CAN bus. The Wi-Fi and Bluetooth functionality is supported by the ESP32 radio module that operates at 3.3 volts DC. The LED matrix is 12 columns by 8 rows, a total of 96 pixels that can be programmed individually or collectively as a frame. The matrix and its API are developed to be programmed in a few different ways, each suited for different applications. The mouse keyboard emulation may be used to build game controllers by emulating a mouse and keyboard. This particular topic will not be discussed further in this video. The microcontroller, Renesas RA4M1, and the general purpose input-output GPIO pins operate at 5 volts DC. The ESP32 module on the board operates on 3.3 volts DC. The ESP header located close to the USB-C connector is 3.3 volts DC only and should not be connected to the 5 volts DC to avoid damage to the board. The Qwiic connector on this board is connected to a secondary I2C bus on this board. This connector is 3.3 volts DC only. Connecting higher voltages may damage the board. To initialize this bus, use the wire1.begin function call instead of that used for the primary I2C bus on the board. The UNO R4 has a maximum current draw per GPIO pin at 8 milliamps, which is significantly lower than previous versions. Exceeding this limit may damage the pin on the board. The Arduino Ethernet shield connects the board to the local area network. Since the UNO R4 Wi-Fi has the ESP32 interface for Wi-Fi, only applications where an RJ45 cable connection is desirable, this shield may serve the limited purpose. It comes with an integrated micro SD card slot that is popular for local storage of data logs. The motor shield is a dual full bridge driver to interface to relays, solenoids, direct current, and stepping motors. It can drive two direct current DC motors controlling the speed and direction of each one autonomously. The Arduino relay shield drives high power loads that cannot be controlled directly by the UNO board owing to current and voltage limitations. The shield provides 4 relays. There is a status LED for each relay. The 9-axis motion shield uses the BNO 055 sensor to provide accelerometer, gyroscope, and geomagnetic data in 3 dimensions for each set of 3 attributes. The common terminology for the sensor is inertial measurement unit, or IMU. The OEM vendor's driver library provides signals such as linear acceleration, rotation, and gravity data. There are 4 options to develop sketches for the UNO R4 board. There are 2 types of integrated development environments, IDE, a legacy and a new and improved, as they say for household products. Then there is the cloud editor and the command line interface. To run extended sketches on the board, there will be a need for support libraries. Arduino provides a few of these libraries. Other libraries may have to be obtained from other sources for any additional hardware that is deployed for projects. There is an experimental user interface to generate the underlying bitmap of images for the LED matrix. This user interface is called the LED matrix editor. The open source Arduino Software Integrated Development Environment, IDE, makes it easy to write code and upload it to the board. This software can be used with any Arduino board. The IDE contains a text editor for writing code, a message area, a text console, a toolbar with buttons for common functions, and a series of menus. It connects to the Arduino hardware to upload programs and communicate with them. Programs written using Arduino Software IDE are called sketches. Instructions on installing the IDE for Linux, Windows, and Mac are described in detail at the Arduino website. The Arduino IDE 2 is an improved version of the legacy IDE with increased performance, improved user interface, and many new features such as auto-completion, a built-in debugger, and syncing sketches with Arduino Cloud. Unfortunately, at the time of preparing this presentation, there is no support for this IDE on ARM64 or AArch64 hardware. In other words, you cannot run this new IDE on a Raspberry Pi single board computer. Let us look at the Arduino IDE version 2. Verify and upload. These buttons compile and upload your code to your Arduino board. Select board and port. This drop-down list displays the detected Arduino boards along with the port number if assigned. Sketchbook. This button leads to the current folder where you will find all your sketches locally stored on your computer. Additionally, you can sync with the Arduino cloud and also obtain your sketches from the online environment. Boards Manager. This button browses through Arduino and third-party packages that can be installed to support the boards. Library Manager. This button browses through thousands of Arduino libraries made by Arduino and its community. Debugger. Test and debug programs in real time. Open Serial Monitor. Opens the Serial Monitor tool as a new tab in the console. Search. You can search for keywords in your code. The cloud editor, as the name implies, runs in the cloud, but has the familiar IDE user interface. The biggest advantage of the cloud editor is naturally not to have to worry about downloading support files to your desktop for development work. All files need to run supported boards and libraries are accessible without having to worry about installing or upgrading these on your desktop or notebook or laptop. Unfortunately, I did not have a good experience with it during the pre-release beta phase. After then, I was asked to sign up for a paid plan. So I have stayed away from this software. If you can get your school or company to work with Arduino for the best option, then you should explore this option. You will definitely be more productive with this software. The ability to monitor one's UNO R4 board from a smartphone app is a big advantage for those who are not experienced in smartphone app development. Of course, be aware of the fine print when you sign up for the cloud editor. The Arduino Command Line Interface, CLI, is an all-in-one solution that provides boards and library managers, sketch builder, board detection, uploader, and many other tools needed to use a board and platform from command line or machine interfaces. There are installation scripts for ARM and ARMv6 architecture in 32 and 64-bit versions. Some transformations are performed before the sketch is passed to the compiler. Pre-processing is limited to files that have the .ini or .pde file type extensions. The dependency resolution sequence is core builder folder, variant folder, standard system directories, and included search paths added to resolve prior dependencies. The compilation is performed by architecture-specific versions of the GCC and G++ compilers. The sketches are uploaded by the platform-specific tool, AVR-Dude, which renders the output to the console window based on command options. One important point to note about this utility is that it is available in two primary flavors: stable release and nightly builds. Naturally, you should choose the one that works best for you. Personal productivity or bleeding edge, as the saying goes. The wire library communicates with I2C devices. I2C is a very common protocol primarily used for reading and sending data to and from external components that support this protocol. The wire library implementation uses a 32-byte buffer, therefore any communication should be within this limit. Exceeding bytes in a single transmission will just be dropped. The I2C protocol involves using two lines to send and receive data: a serial clock pin, SCL, that the Arduino controller board pulses at a regular interval, and a serial data pin, SDA, over which data is sent between the two devices. In I2C, there is one controller device with one or more peripheral devices connected to the controller's SCL and SDA lines. The availability of secondary interfaces for I2C, Qwiic, with its 3.3 volt restriction, and the digital header for general purpose connection highlight the careful design considerations by Arduino for this very important interface for diverse applications. Serial Peripheral Interface, SPI, is a synchronous serial data protocol used by microcontrollers for communicating with one or more peripheral devices quickly over short distances. The SPI library is included in every Arduino core platform. It does not have to be installed separately. The servo library allows Arduino boards to control servo motors. The library can control up to 12 servos using only one timer. It would be impractical to demonstrate all the features of the UNO R4 board in a single presentation. Not only would we have to cover 2 decades of UNO examples, but the R4 new features themselves demand time beyond the practical limits of this presentation. Therefore, the list of demonstrations is limited to features that were not available in previous UNO boards. The LED matrix can display graphics and animations. The matrix and its API are developed to be programmed in a few different ways, each suited for different applications. The ESP32 module supports Wi-Fi and Bluetooth. If the interests of video length or duration, there is no demonstration of Bluetooth functions in this video. The digital to analog converter, DAC, transforms a signal from digital to analog. This feature can lead to interesting audio applications and also serve as a function generator for projects. In order to use the real-time clock comprehensively, it is necessary to apply a voltage in the range of 1.6 to 3.6 volts DC to the VRTC pin. The Qwiic connector uses the I2C protocol to connect peripherals or sensors in a daisy chain series from a single port on the board. The controller area network, or CAN bus, for the UNO R4 board needs an external transceiver such as the SN65 HVD230 breakout board to communicate on the bus. After connecting the UNO R4 board for the first time, one has to go ahead and install the support for the board. So we would click on the toolbar on the left and we will refine our search for UNO R4. And sure enough, you can see that it has not been installed, so we can go ahead and click on the button to install it. It just takes a few seconds for the installation process to complete. And once that's done, we will do the simple blink test to verify that the board is now operational. So the success message was displayed. I dismissed it, and let's just click on this, and we're ready to now go and select the board. So we would go to board and select from boards manager UNO R4 boards. So I'm going to go ahead into screen mode because the drop downs don't show up easily when I'm capturing the windows. Let's go ahead and select the board from the board manager, and you can see that we have here the UNO R4 Wi-Fi is what we're going to be testing. So we select that, and I know ahead of time that it's on ACM1 for the port. So as you can see, it shows me clearly ACM1 UNO R4 RPi. Let's load now an example, And we'll just load the basic blink example, which is the simplest case, just to establish communication between the desktop and the board. The header permits the instantiation of the LED matrix entity in the sketch. The frame is the buffer to retain the display state of the LED matrix. While it is simple to assign a byte or an integer to represent the state of the individual cells in the LED matrix, that would be a waste of precious RAM when the state is simply on or off for a cell, a 0 or 1. We will review this design option in one of the initial examples for the LED matrix. The data in the buffer can be scrolled in either horizontal direction, left or right. Arduino has provided a set of frames for use in sketches. Arduino has also enabled access to an experimental method of generating frames using the animation generation editor. Before we can start working with the LED matrix, we need to ensure that we have the right support libraries installed. So if we go to the board manager and type UNO R4, it will list the board manager, and you can see it's been installed already, so we don't have to do anything. Similarly, we can go to libraries and look for UNO. Since we're not concerned about the BLE library, we can ignore that, and by default, Arduino would have installed all the support libraries for the LED matrix during the board installation. Now, the main statement is the header file that is shown here, which is Arduino _LED matrix.h. And we have to include that for all LED matrix operations. What happens is that gives us the chance to instantiate an entity called matrix here that we've defined, which is our user variable, and we give it the type, which is Arduino LED matrix, and we can start using it in our code. In the setup, naturally, we say matrix.begin, and then we start loading the frames. So in order to display in a very simple way, all we have to do is define a frame, for example, chip in here, and load it with our entity matrix, and the function is load frame. So we have chip, danger, happy, and LED matrix, big heart in this short demonstration. So before we can run the demonstration, I'd like to spend a few seconds going over what makes a frame for the UNO R4. You may have noticed that in this sketch, I have a second tab called frames.h. So let me go ahead and click on that. In case you want to know how to create a tab, you can go to the right-hand side on the tab bar and click on the ellipses, and you can see I have a new tab. Once you click on new tab, you can give it a name, and then thereafter Arduino IDE will use it to when you're compiling the sketch. So let's take a look at how we want to encode the frame for a heart. If we suppose, for example, for discussion purposes, this is what we want to do for our heart to look at. It's a very simple thing. The dots represent no light. In other words, the LED is off, and the X represents the LED is on. So you can see when the LED is on, it'll appear a very simple heart shape on the screen. Now, this is a 12 columns by 8 rows. In other words, it's 96 LEDs, but it's arranged in 12 by 8. So if we were to now spread that out and convert it to 32 columns by 3 rows, then we still end up with 96 LEDs. And the convenient part about the 32 is that we're using a 32-bit microcontroller, so one word on that microcontroller is 32 bits. So all we need are 3 words to represent the frame in the buffer. Now, if we take our hard data that we have here and convert that to zeros and one, which is on or off, then the equivalent binary representation of our heart shape will show up here in this line that I've labeled as binary. If I scroll down a little bit further and divide it into hexadecimal, in other words, 8-bit numbers, 1 byte at a time. So if I spread out, all I did was I went in here and I put a space in between to push it out, and I still have 96 bits. But now I have a convenient representation to convert it to hexadecimal. So this byte becomes 31 hex. Similarly, this one, if you know your binary or hexadecimal arithmetic, you'll see it's 84 and so on and so forth, right? That is converted into hexadecimal representation in these 3 lines in here. So in order to define the frame, I'm going to scroll down here a little bit and show you that that is exactly what we've done for the heart. So for the heart shape, we have representing it with 3 words, a total of 96 bits, but in its representation. Now, obviously, this is a little messy, and there are better ways to go about doing this that I'll show you later on in the demonstration. But for now, I think this should suffice as to how I get the data, frame data for the chip, how we get a frame data for the danger sign, how we get the frame data for the happy sign, and then obviously we've drawn conclusions regarding how to show up the heart. So back to our code again, and as we mentioned previously, we're going to go ahead and ensure that the matrix is the entity variable that we're going to use, which is of the type Arduino LED matrix. And we initialize it with the matrix.begin command in here, and then we load each frame and have a 1-second delay between successive frames inside the loop. So matrix.loadFrame, chip, danger, happy, and LED matrix, heart, big. So I hope you understand how the frames are created, and obviously it's very easy to do this if you know how to fill up a frame buffer. But obviously most of you would prefer to do it using the Arduino supplied LED matrix editor that we will examine in a later demo. There is a reason why this frame is shown in uppercase. We will get to that later in our subsequent demos. But for now, let's verify that the sketch is correct. And we click on the verify button on the top left hand on the toolbar. And once that's complete, it gives us the message done compiling. And now we need to ensure that we have the right board and port selected. In this case, it's UNO R4 on ACM0. So we'll go ahead and perform the upload operation by clicking on the second from left button. And it's going to go through the process, and it's done. So it's done uploading. Now let's go ahead and look at the board. Now that we know how to display one frame at a time, in other words, static display of frames, let's go ahead and look into something more dynamic. The Arduino UNO R4 LED matrix permits scrolling of text to left or right. And in this sketch here, we are going to show you 2 examples. One, what happens if you don't scroll? And secondly, how do you scroll? So the key thing is to include the Arduino graphics library and then to instantiate the entity, and we call it matrix again just to keep it simple. And for the display where there is overflow of text, the full text cannot be displayed, but there is no scrolling, we have chosen the text UNO space R4 to be displayed on the screen. And as you'll see in the subsequent demo, because of the number of characters that we have here, we can only see UNO displayed on the screen. The space R4 does not show up. So in order to get it scrolling, we'll just use the classic phrase hello world for the demonstration. So we instantiate the matrix and say begin draw, and we set up the scroll speed with the function text scroll speed. We choose a buffer for the text, and we define a font, and with that we initiate the scroll, and we can do a scroll left or scroll right. And for confirmation purposes, of course, we naturally want to have it displayed on the serial monitor if there is a need for that. But notice that the matrix function uses a println or print similar to what the serial monitor does. So that's an easy way to transfer your text from the serial monitor code or sketch to the display in the new UNO board. So we'll go ahead and compile this. We just make sure, first of all, that we are connected correctly, and we go and verify the code, and it's done compiling, and we'll go and now upload it. And in a few seconds, it'll upload it. And once the upload is done, as it says here, let's go ahead and look at the board. Once the upload completes, in the sketch setup, UNO space R4 is displayed statically. Since there is no space, only UNO was shown. In the loop section, hello world scrolls to the left as indicated in the sketch. Arduino provides a series of frames in what is known as the frame gallery, or preset frames that you can invoke in your sketch without having to define the frames yourself. And if you notice, this is why in our first example we had the heart in uppercase. Although I did show you how to define the heart as a frame, we were actually using Arduino's definition of that frame. So in this sketch here, again, there is no need for any other library other than the LED matrix, and we instantiate the matrix and initialize it using the begin statement. And in the loop, we cycle through each one of them. So there's Bluetooth, bootloader on, chip, cloud Wi-Fi, twice, danger, emoji happy, emoji sad, heart big, heart small, like, music node, resistor, and of course UNO. So you can use these without having to worry about creating frames for their use, and hopefully it'll be very useful for you in your applications. In the first demonstration of the LED matrix, I showed you how to create a frame. And obviously, it's a little tedious. So what Arduino Labs has released an experimental software called the Arduino UNO R4 LED Matrix Editor. So if you go to Arduino Labs, which is labs.arduino.cc, and then in the middle pane, click on the LED Matrix Editor, and you are then sent to this page where more information is available on the LED Matrix Editor. While I'll leave it to you to read this at a later date, let's go ahead and look at what the editor looks like. So click on this, and up here is the editor. So the key topics here, this is a 12 by 8 LED matrix equivalent, and there are some toolbar buttons in here, and we're working on the first frame here. So I can go ahead and click on this frame, and if I want to erase it, then I go and select the erase button, and then I deselect it. So let's go back and create the first frame. So what I want to do is I put this in here, and that becomes my first frame. In my second frame, what I like to do is click here and then put it as my second frame, right? And then in my third frame, I'll go ahead and do this, and that's my third frame. In my fourth frame, so I have 3, and then I have that, and then finally I have this, right? And then I can go and extend this concept even further. And you get the idea here. So we can click on the play button to view the results of our frame by frame animation. And hopefully it should look satisfactory to you. At this stage, we have the option to save the project on our own desktop by downloading it and overriding the default name if appropriate. So go ahead and type a file name and click OK, and depending on your operating system, it will be deposited in the appropriate downloads folder. You can also download the header file, the .h file, by clicking this button, and please give it a name which is unique for your purposes. There should not be any spaces in the name, because that name will be used as the frame buffer name as a C or C++ variable. So type the name. Here we're typing in gradient descent, and we'll click the OK button. Now this file is downloaded to your downloads folder, and you will have to move it to your Arduino sketch folder, as I'm showing you on the screen here shortly. After moving the file, you can examine a simple animation sequence as an example that I'm using here to just display each frame by frame, load it into the frame, and cycle through in the Arduino sketch loop function. So nothing special required, because we don't have to read anything. We just include the file. It's a header file. And then we have a nominal variable to compute the number of frames so that we can loop through the number of frames. And here you see the frames that were created and downloaded in the gradient descent.h file. And essentially, this is a very simple and easy way to examine the results of the animation in what we would call batch mode. If you want to do it in real time, Arduino LED matrix editor has a simple sketch at their website that illustrates how to send the frame data directly to your Arduino sketch so that you can display it in so-called near real time. I will not demonstrate that here for obvious reasons, but clearly it's another option for you to examine your animation in near real time. And once we upload the code, you can see now that the animation works exactly like we saw it in the LED editor. So I hope this was useful for you in terms of working through the LED matrix. Naturally, there are possibilities that are beyond the coverage of this simple tutorial. Some of the Wi-Fi exercises that we will explore in this tutorial are listed on the slide. Scan Networks publishes the list of available networks but does not connect to any access point. Connect to access point uses specified credentials to connect to an access point and publishes network connectivity information. Web client connects to a well-known site to demonstrate HTTP header data in messages. The UDP NTP client is a useful introduction to leveraging the onboard real-time clock for future applications where time synchronization from a reference server or perhaps even a GPS satellite may be desirable. Naturally, these examples are simply to illustrate the diverse potential of the UNO R4 board. Sorry for repeating myself. There are many examples, even at the beginner level, that one can explore with the UNO R4. The first sketch for this demonstration of Wi-Fi networks naturally would be to scan for existing networks. This is from the Arduino example set. The only modification that I've done is to display some of the information in the LED matrix. The extra library that is needed for Wi-Fi support is Wi-Fi S3. And you can include the header file, and that will automatically allow us to make use of the extensive Wi-Fi library for the UNO R4. Nothing much has been changed except that if the Wi-Fi is not detected, then it displays a status message on the LED matrix. And then it'll start scanning, and while it's scanning, it displays a scrolling text on the LED matrix. Once that is complete, then it'll summarize the number of SSIDs it found on the LED matrix. A lot of information is presented in the serial monitor, and if you are interested, you can pursue that. Since most of the information that is detected in this network is of no use or relevance to anybody else, I've decided to not present it in this tutorial. So again, it's a simple tutorial, just trying to show you how to adapt very quickly existing code snippets for the LED matrix into the Wi-Fi examples. So obviously the first thing we do once we are satisfied with this sketch is to verify for compilation. Once done compiling is complete, then we make sure we are attached to the right port for the board and upload the code to the board. This just takes a few seconds again, and once it's done, we can view the output on the LED matrix to the extent practical. And as you can see, it's sending the scanning, and now shortly it will summarize the number of SSID points that it found. And this is 10 for now. So that's it, and you can look at the serial monitor if you're interested. In the last demonstration, we showed that the UNO R4 board, with its built-in Wi-Fi support, can detect existing Wi-Fi networks. And for demonstration purposes, at that time, we saw that there were 10 SSIDs available. So let's go ahead and connect to one of these. So in order to connect to one of these, we have to know the SSID and we need to know the password also. It is not a good idea to have it in the main sketch, but it's best to use a separate tab where you define the variable and you enter your SSID and you enter your password in there, and then in the main code it's referenced automatically through the include statement that you have as secrets in here, right? I'm not going to change anything with this code anymore, because all I want to do is show you that now the UNO R4, given the SSID and the password, will be able to connect to the correct network. After we have entered the correct SSID and the corresponding password in the secrets tab, let's go ahead and compile. And it's done compiling, and the next step, of course, is to upload to the board. Now it's done uploading, and as you can see, it is going ahead and displaying the information about the connection to the network. In the third example, again, straight from the Arduino examples, we are going to use a simple web client to connect to a well-known established website. So we have the library included, and obviously our SSID and the password is in the secrets tab. And then the website that we want to connect to is www.google.com. And it's going to return a bunch of characters and strings. We're not going to format the message, but we'll display it in the serial monitor. So let's go ahead and compile for validation. And it compiled fine. Let's make sure that we're connected correctly, ACM1. And now we'll go ahead and upload. Once the uploading is complete, expand the serial monitor, and you should be able to see a whole bunch of text that comes up. So it gives us the SSID that it connected to, the IP address, a couple of other information about the connection, and then we're using HTTP and not HTTPS. And there's a bunch of header information for HTTP, and then obviously the HTML document that has been returned is displayed here in great detail. Now, this is not an exercise in understanding what HTML can be rendered as, but hopefully you get the idea that we made a valid request to google.com and we got a reply using this web client running on UNO R4. In this sketch, we will demonstrate the use of a very simple UDP client to query the network time protocol server. The network time protocol server that we will query is 162.159.200.123. It serves as a pool of servers, and since we are not using DNS name resolution, we have to specify the IP address explicitly. We also have to use the port 2390, which is reserved for UDP packets sending NTP messages. Once we run this, we will get the latest Unix time from that server. Now, we can save that time in the RTC, the real-time clock on the Arduino, if we have a battery attached to it, and thereby use that as a reference server for our local area network, or to serve any kind of task on the Arduino that requires real-time information. So let's go ahead and compile. And now we can go ahead and build. So the upload is complete, and we can now go to the serial monitor and look at it. So you notice that the system returns the Unix time in here, and we convert it to local representation, which is almost correct based on the data that I am showing on my desktop. So this continues consistently, and of course it is a good idea to save this information on the real-time clock. Using a digital pin to turn on and turn off at precise timings, it is possible to emulate an analog output. This is the basis of pulse width modulation, PWM, that is popular for applications requiring a controllable output voltage. Some examples of such use are dimming LEDs or changing the speed of motors. However, for some applications, a true analog signal is required. For example, PWM cannot provide the proper input for audio output. The sound quality will have low quality since it will not be a sine wave harmonic. Using the DAC output from the UNO R4 board, a sine waveform can drive the test speaker to generate sounds and simple melodies. While it is possible to use the piezo buzzer without the additional circuitry, using the device without additional circuitry should be limited to hello world exercises. Ideally, to hear the best results, the piezo buzzer should be replaced by a basic speaker. Unfortunately, that is for me personally, extra circuitry is required, and I will leave it for a future exercise. In this demonstration, we will look at the built-in digital to analog converter, which can be used to transform a digital signal to an analog signal. This feature can be used to build audio projects. It can also be used to simulate cheap function generator at your desktop. The demonstration will use the UNO R4 with a piezo buzzer, a potentiometer on a breadboard. We could do the same thing with pulse width modulation, but the sound, if you are very careful, will not be as pleasing as that produced through the use of the digital to analog converter, because we will have a pure sine wave generated by the digital to analog converter. Here is the breadboard representation of the sketch that we want to run. So we have a UNO board, we have a potentiometer, and we have a piezoelectric buzzer. Unfortunately, I couldn't find the right part for a UNO R4 in the Fritzing parts library. Neither could I find a suitable piezoelectric part. So please bear with me for the shapes. The connections, of course, are appropriate. So in the case of the UNO, the potentiometer is being driven through this A5, which is the middle point, and that gives us the reading for the potentiometer setting. This is converted in the code into a signal which is fed through the digital to analog converter pin, which is A0, to drive the piezo. The piezo is grounded, and the potentiometer, of course, has 3 leads. So it's a very, very simple sketch. And what we do is when we run the sketch, we turn the knob clockwise or counterclockwise, and we've arbitrarily set the range between 0 and 1024 units for the potentiometer. So we map that to a value, whatever reading we get of the resistance. This is in fact a 10K potentiometer, but that's irrelevant for the purposes of our demonstration. So the value that we get out of the potentiometer, we map into a range of 0 to 1024, and we feed that as a frequency to the analog digital converter, and the output from that pin on A0 drives the speaker with a pure sine wave. Let's look at the actual board now. So obviously we have the UNO R4, we have the piezo buzzer, and we have the potentiometer. The potentiometer has the connection to A5 pin, which is the blue wire, to the middle setting of the potentiometer. The piezo buzzer is driven by the A0, which is the digital to analog, and it's connected here. The rest of the stuff is all ground and positive. So very simple connection, and all you have to do is rotate the knob to get the varying frequencies. Let's go over the sketch now. The first part is to include the header file for the analog waveform generation library. And we can instantiate an entity called wave for the analog wave class, and we'll use the digital to analog converter pin, which is A0 in this case here for the UNO R4. We initialize the frequency with a nominal value, and then in setup, we generate the sine wave with that initial frequency that we've just set up. Then we go into the loop and read the potentiometer setting and map that to a value in the range of 0 to 1024 and apply that frequency to the buzzer. Have a delay of 1 second in between, and then repeat that with the new reading from the potentiometer. If at all we've changed it, that'll be reflected in the serial output, as I'll show you in a few minutes, or it'll continue with that same frequency. So let's upload the code, ensuring that we have the right board and port identified. Click on the button, and it's going to compile the code and give us the output in a few seconds. And now the code is running, so I can open the serial monitor, and you can see that it's giving us a certain frequency value. If I go ahead and change the potentiometer, the readout will change. At the upper end, we have 1024, and at the lower end, we have 0 for the potentiometer. And if we turn the knob, the values will keep changing, as I can show you in here, right? Another way to look at it would be to launch the plotter view and turn the knob. And as I turn the knob, you can see that the value goes up or down, and the axis is in the range of from 0 to almost 1024, right all the way to the top. So I hope that this gives you a very simple understanding of how useful the digital to analog conversion can be for your audio projects and for any kind of waveform generation that you want to do in the lab. This demonstration will use the real-time clock to retrieve and store time from a network time protocol, NTP server. Retrieve the time from the real-time clock. Set the time on the real-time clock. Establish periodic interrupt for recurring notification using a callback function as the interrupt handler. Set an alarm function. In this demonstration, we will use another Arduino example to show how the real-time clock, which is something new on the UNO, can be used to set the time, and thereafter, once it's set, it'll keep track of the time provided a battery is attached to it. In the demonstration, all we're going to do is to set the time from a reference clock, and then I will show you separately how to attach a battery so that the time can be preserved. Now, the battery is not really the most desirable example that I have for a battery, but I hope you'll get the idea. So let's go ahead and look at the code. It requires a new library that is supplied by Arduino, NTP client. And then, of course, we have to use the secrets tab to preserve our SSID and password from snooping. But the program will pull it in through the declaration. And then we will just upload the sketch and look at the serial monitor output. So as an example, let me just go ahead and compile this and show you the first error message, which obviously tells us exactly what we need to do, which is to install this NTP client. So we go over to the library folder here, and then we look for only Arduino code, otherwise there'll be a massive amount, and we type in, for ease of search purposes, something like NTP, and immediately the NTP client comes up, and its version 3.2 is the latest one. So we'll go ahead and install that. And once the installation is done, we can just close the tab and then compile again to show you that now the compilation will proceed as required. So very shortly, it'll say done compiling. And now we can once again compile and upload to the board, assuming that we have not changed the connection of the board, which in this case seems to be exactly how we're expecting it to run. So it's done uploading, and now we can open up the serial monitor and look at the output in the serial monitor. So let me go ahead and check and make sure that the serial monitor baud rate is correct. As you can see, obviously it's not. I have it set at 1152. So let me go ahead and change this to 115200. And rebuild again, upload. Sorry about that. I should have checked that before doing the upload. But here we go. Now it's done, and it should start sending us the message. And sure enough, we get summary information listed. And here's the information. It's connected in the Wi-Fi. It's connected to access point. It has the IP address and the Unix time. And this is clearly, 717 in UTC. So it's 135. And I hope that gives you an idea that we're on the right track in terms of using the RTC. I don't want to get too much into the business about NTP servers and NTP pool, but just want to quickly go through the code and show you a couple of other things that are should be of interest to you. Number one, we're using a very, very generic pool for the NTP server, and you may want to use one of your preferred servers in your region, or even, for example, your university, where that information is saved. Once that's done, then it'll go ahead and collect, and maybe perhaps I should print out the NTP server that it's using, but you get the idea. The key command in here is once it gets the time, it uses the NTP client library to set that time to the time that it was retrieved from the NTP server. The library has this pool, and it's the most common pool, but obviously, if you are in the US, you can type in us.pool.ntp.org, or even, depending on your operating system provider. Ubuntu, for example, maintains its own NTP servers. You could, for example, also, provided you have an accurate Stratum 0 clock, which is difficult to get, but even a Stratum 1 should do the job for you. So now that you recognize that we can retrieve the correct time and then save it on the UNO R4, obviously if we turn the power off, then we're going to lose that setting. So we have to have a power source to the real-time clock. And in the next section, I will show you the pins that you can use to attach a battery and preserve the time on the RTC chip on the board. So there are two pins of interest. There is the pin marked VRTC, and that's the positive power that's applied, and that's why I'm using a red cable. And next to it is the ground. And as you can see on the board in here, I have a terminal and I have a battery. This battery is really overkill for an RTC. A small coin battery should do the job, and it should last many years because the current draw is of the order of a few microamps. But if you don't have this connected, then as soon as you turn the power off to the UNO, that setting will be lost, and you'll have to reset it every time you run your UNO. And that's not a problem because you have Wi-Fi again, and as you can see in the simple code, it's very easy to retrieve the current time and set it in the clock, and thereafter keep maintaining it. So whichever way you want to do it, perhaps, even the Raspberry Pi 5 now has an RTC on board, and very soon it'll become a de facto standard almost in all low-end single-board microcomputers. So I'm not going to get into how to retrieve the time. It's a simple function call. And similarly, you can set up an alarm callback also with this RTC. So that's another useful function to have if you are doing some monitoring and you want an alarm at a certain designated time slot. Then there is the function available that will allow you to do that very easily. I hope this has been useful and that you can make better use of RTC, and perhaps you can brush up on your knowledge of a little bit on NTP, and of course we used UDP for this purpose. On the subject of real-time clocks and batteries, allow me to digress a little bit and show you what I normally use for the Raspberry Pi. So for the Raspberry Pi from 1, 2, 3, and 4, here is a commercially available real-time clock chip that one can just plug and play. Play is not necessarily the right word because you'll have to do some configuration, but as you can see, the 5 pins are fully compatible with the Raspberry Pi header. I've removed the real-time clock board and flipped it over to give you an idea of the size of the battery that would normally power this board when the computer is offline. It's a very small battery, and therefore there should not be any misunderstanding regarding my earlier demonstration with the battery that was at my disposal for the Arduino. So here we have the 5 pins. The first one is the 3.3 voltage. The second one and the third one are for the I2C pull-up interface is GPIO2, which serves as the serial data line, and then GPIO3, which serves as the serial clock line for the I2C interface. The fourth one is ignored. It's not used. It's really a dummy for all practical purposes. And the fifth one is ground. So I hope you understand that the smallest battery possible, if you can connect it, should do the job for you. Unfortunately, there is no ready-made solution for the Arduino in the market, so you may have to practice some soldering and getting the right wires. The Raspberry Pi uses the external battery as shown here. If you notice at the jumper connection here, it's a 2-pin jumper connection, but it will not fit directly plug into the pins for the same purpose on the Arduino UNO R4. So you will have to just cut this and prepare your own JST 2-pin connector if you can. If not, you can look at some alternate methods that I will show you that I have on the board in here. But this battery is very popular for motherboards where the coin battery is not socketed onto the motherboard. So like Alienware, Dell, you name it, a whole bunch of motherboards use this connection, and maybe that's why Raspberry Pi Foundation decided to use this particular jumper instead of the standard JST 2-pin standard that we're accustomed to. So back to our UNO R4 board, you can see I have a slightly different battery, and the only reason I'm demonstrating this is that the range of voltage that you can supply to the VRTC pin out here, that ranges from 1.6 volts to approximately a little over 6. So there are a wide range of batteries that you can use or sources of positive power for to support your real-time clock when the Arduino is offline. So far, it's all been positive about the built-in real-time clock. But now, let's change the tune a little bit. I've been running this in a loop for over 20 minutes now, and clearly there is a discrepancy between the date timestamp from the desktop, which is relatively stable, and the time reported by the RTC on the Arduino board. So here's what I mean. Let me freeze the frame here. And you can see that we started off at the same time. By the way, 1600 hours is my local time, 2100 is UTC, so I'm 5 hours behind UTC. You can see that the minutes has changed a little bit because I've been running this for almost 20 minutes now, a little over 20 minutes. But more significantly, you can see that the seconds is totally out of whack. And I estimate that roughly for every 2 minutes, the clock is gaining, the RTC on the Arduino is gaining an extra second. This is undesirable, and it may make practical applications difficult if you were to just set the time once in the setup section and not set it again in the loop. So here's what we're going to propose. We're going to go ahead and revise the code, and instead of just setting the time as I'm showing you here in the setup section, which is what I have here, the setup, I'm going to go ahead and repeat this code in the loop, and then we'll run it for 20 minutes or so and see what we get. So stay tuned. I've modified the code to set the time in the loop section of the sketch. So we go ahead and call the NTP pool and get the value and then set it. If you look at the bottom, let me freeze it for you a little bit. You will see that there is hardly any discrepancy in the seconds, let alone the minutes and the hours, of course, between the date timestamp on the desktop and now the value reported by the RTC on the UNO. So this is one way to do it. You don't have to do it probably more frequently than 30 seconds or so, but it doesn't hurt. The other point that I want to make is that maybe perhaps if you have a GPS module, a luxury of having a GPS module, these are like $5 or $6 nowadays, you could get a more accurate time direct from GPS and not have to call the NTP server, which sometimes, depending on the server pool that you're calling, they may get a little annoyed if you're calling it every second or so. It doesn't happen very frequently, but they may just drop the connection. That's all. So no damage there. Perhaps NTP is a much more universal solution than trying to rely on GPS. So the solution for using RTC in a practical way is that you have to set the time within the loop section of the code and not just the setup section. So hope that helps, and we'll now move on to the next set of demonstrations. The UNO R4 Wi-Fi has two I2C buses, and the Qwiic connector is connected to the secondary one. The practical effect of this configuration is that a separate entity definition is needed for sensors using the Qwiic interface. Arduino provides the Wire1 library for this purpose. This library must be explicitly defined using the library name class. This will be illustrated in the example sketch shortly. There are hardware attached on top boards, also called HAT, that can connect to sensors without a daisy chain arrangement. Again, these types of connectivity help IoT makers to spend more time on doing experiments, and they need less time fiddling with wires and breadboards. Truly plug and play. The important point to remember is that the Qwiic interface operates at 3.3 volts DC, while the UNO R4 supports 5 and 3.3 volts DC. Just be careful. Before we do any demonstrations on the I2C interfaces, namely the Qwiic interface, let's go over the I2C interfaces on the UNO R4. We have the traditional old pins still supported, A4 and A5. A4 is the serial data line and A5 is the serial clock line. It's like in R3 and older versions. Arduino has also provided an additional pair of I2C interfaces here right at the top. These are new pins. These pins don't exist on the R3. So this is a new set of pins for the UNO R4. You have the serial clock line and the serial data line. Additionally, there is a second I2C interface, which is the Qwiic interface out here. The Qwiic interface is designed to work with dedicated cables where you will not have to worry about the serial data line or the serial clock line and ground and power. Unfortunately, this diagram does not explain clearly the pin connections, and it may be revised in the future in case you are planning to connect to the pins with your own sensors and you do not want to use the SparkFun Qwiic cables. Ideally, of course, you should be using the SparkFun Qwiic cables. So this is the end that we will be using for our quick demonstration on the BME 680 Bosch sensor, and we'll use the Qwiic interface. When I connect the Qwiic interface, I will show you that this diagram requires a little more clarity because it can be confusing. Before we begin the quick exercise, let's take a look at the hardware. On the Arduino, I'm pointing at the Qwiic board in here. It uses the I2C interface, but as we'll see in the sketch, a slightly different way of calling the wire library is required. The jumper connection is with a standard ground, 3.3 volts, serial data, and serial clock. Black is for ground, red for the power, blue for the serial data line, and yellow for the serial clock line. I don't have any Qwiic devices at the moment. There's still an order, and it's going to be taking a few days for it to come. So when it comes, I'll be able to start the demonstration. But all you have to do is plug it in, and there's only one way to plug it in. You can't plug it in another way. It'll never go in, and this is the only way it'll go in, so you will never mess up your I2C interface. The other thing is that SparkFun provides a whole bunch of other interfaces like jumper boards and hats. This is for the Raspberry Pi, and you can see you have 4 Qwiic interfaces. And the beauty of this is that you can daisy chain a series of Qwiic boards without having to worry about where is my serial data line, what DuPont wire connectors do I need on the breadboard and all that. So it makes it easy for plug-and-play purposes. So as soon as I get the board that I've ordered, which is a BME 680 temperature pressure sensor and humidity, so we'll be able to run some very simple experiments to show you how to use the Qwiic interface. Here is the sensor that we will use in our demonstration of the Qwiic interface. The Qwiic interfaces are at both ends, and as I had mentioned previously, this can be daisy chained, and you can use the Qwiic cable. The BME 680 sensor is right at the center here. It'll measure temperature, pressure, derive altitude for you, humidity, and air quality. It is very small, and it is very difficult to handle discreetly to have it mounted on your board by yourself. So it's best to buy a pre-mounted board for this purpose. The I2C connections are given on this side, and the SPI, should you want to use it, is on the other side. I'd advise you to just stick to I2C. The address for this board from SparkFun for the BME 680 is fixed at 77 hex, and that's marked on the other side of the board. It's written down there. You can look at it, and perhaps in case you want to forget about it, that's fine. You can't change it easily, even though there are techniques to do it. So if you get a BME 680 board from Shenzhen, probably have an SDO line which you can set high or low to change the address from hex 77 to hex 76 in case you want to have more than one, or you want to use 76 as your I2C address. As I mentioned previously, it's relatively easy to connect boards using the Qwiic cable through the Qwiic interface. On the Arduino UNO R4, the Qwiic interface is here. It's the second I2C bus, and we use a Qwiic cable to connect it to the BME 680 board. We could have used either end because the other end can now be connected to other Qwiic supported boards. So essentially, there's nothing much here in terms of wiring. You just plug and then start running the sketch. So in the next slide, I'll show you what the basic sketch looks like, and then we'll go ahead and run it. In order to use the BME 680 sensor, we have to install a library or two for the BME 680 sensor. So let's go ahead to the library and search for the available libraries. Of course, I've gone ahead and installed some of these. This is the most popular one that you see here, BME 680 by this person. There are others, for example, from the manufacturer of BME 680, Bosch Sensor Tech. They have a library. This is slightly old. It's 1.2. I think the later versions are much more recent. And then there is another variation of that library for software development purposes. I have not installed any of the other libraries because you can get carried away and install so many different libraries. Let's just look at Arduino and you can understand why that's the case. Because Arduino does not have any direct support library for the BME 680. So we have to rely on third-party libraries. So now that I've installed a library, the main thing to understand in the code is that instead of using wire 1 for I2C, instead of using wire.begin, I have to use wire1.begin. And that's because the Qwiic I2C interface operates at 3.3 volts and cannot be used with the same interface as we have for the regular I2C interface, which is 3.3 and 5 volts. So that's the only variation that you need in your sketch, and then the rest is common. The address, again, is 77 that I'm using, which is the standard default one for the SparkFun BME 680 board. So let's go ahead and run this and then see the results. As soon as we upload the sketch, the BME 680 sensor is detected, as you can see in the serial monitor, and immediately it steps through a loop reporting the temperature, humidity, pressure, altitude calculation, and the air quality. And the loop count is on the first column, and the other variables are written on the subsequent columns, and every 25 iterations, the header is repeated again, just to help you follow it. Obviously, this is a very, very simple way of looking at whether the BME 680 is working or not, and thereafter you can modify the sketch and upload the telemetry data to a source of your choice. A controller area network CAN is a vehicle bus standard designed to enable efficient communication primarily between electronic control units, ECUs. This broadcast-based message-oriented protocol ensures data integrity and prioritization through a process called arbitration, allowing the highest priority device to continue transmitting if multiple devices attempt to send data simultaneously, while others back off. Its reliability is enhanced by differential signaling, which mitigates electrical noise. The CAN bus has 2 pins on board, D13 to receive, D10 to transmit. The UNO R4 requires an external transceiver to support CAN bus. One example of this transceiver is the SN65 HVD230 module using a Texas Instrument chip. I would like to demonstrate this feature at a later date with a planned interface to an Arduino Giga that has the transceiver on board. In other words, the Giga does not require a transceiver, but the UNO R4 does. Let us use a breadboard layout diagram to understand the proposed scope of the CAN bus demonstration. The UNO R4 will act as a CAN bus node. Please bear with me for this image of the UNO R3 board. I could not obtain an image for the UNO R4. Therefore, I am using the image for the UNO R3. Please accept my apologies. The two boards are pin compatible for our demonstration purposes. There will be a need for another node on the CAN bus to receive the message from the UNO. Of course, there can be more than two nodes attached to the CAN bus. This is precisely why it is called a controller area network, CAN. Automobiles have many nodes which are referred to as ECU, Electronic Control Unit, in the manufacturer's documents. Manufacturing factories that deploy CAN bus technologies will have a significant number of nodes too. In our demonstration, in the spirit of Hello World demonstrations, we will use the Giga R1 board as the second node. It too supports CAN bus messaging. To keep things simple for this first CAN bus demonstration, we will limit ourselves to only two nodes. The Giga will receive the messages from the UNO. It will not send any messages. We don't connect the two Arduino boards directly. We rely on transceivers to control the data flow on the CAN bus. I have chosen the popular SN65 HVD-230 transceiver for this purpose. There are many excellent CAN bus transceivers in the market. We use two of the chosen transceivers to act as the intermediary for the messages. One transceiver for one node. Before we dive deeper into the breadboard layout diagram, let us take a quick look at the pins on the SN65 HVD-230 transceiver. It has 4 pins on the lower edge and 2 pins with the twin terminal block at the top edge. Facing the board, the 4 bottom pins from the left are 3.3 volts, ground, CAN RX for receive, and CAN TX for transmit. Still facing on the top, the 2 top pins from the left are CAN L and CAN H. And of course, you can connect wires at the top here. Unfortunately, I could not find a suitable fritzing part for the UNO R4. Arduino, I believe, is no longer interested in providing fritzing parts during the launch of their boards. Since the UNO R4 is over a year old and there has been no published open source projects in the fritzing gallery, it would be more expedient for the current demonstration to use equivalent UNO R3 part, which is pin compatible with the UNO R4. The 4 pins on the UNO for this demonstration are 3.3 volts, ground, Digital 13, the blue, which is CAN RX, and digital 10, yellow, which is CAN TX. Note the color conventions that I am using for this demonstration. You may have other preferences. The D13, the blue wire, is connected to the CRX pin on the transceiver assigned to the UNO. D10, the yellow wire, is connected to the CTX pin on the transceiver assigned to the UNO. Fortunately, some good Samaritan took the time and effort to create a fritzing part for the Giga board, which I'm using in my layout diagram. The 4 pins on the Giga for this demonstration are 3.3 volts, ground, A14 for CAN RX, and A15 for CAN TX. In keeping with the chosen color convention, A14 is the blue wire and A15 is the yellow wire. Both wires are connected to the transceiver assigned to the Giga. Let us now explore the CAN bus connections. Before I drill down, I want to draw your attention to the color code convention that I have adopted for this demonstration. This convention is summarized on the right. I have taken advantage of the bus layout of the board. There are 2 pairs of buses. One pair is used for conventional power and ground. The other pair is used for CAN low and CAN high connections. Just think of 2 sets of parallel wires. One wire representing CAN low and the other represents CAN high for the CAN bus. You may have noticed 2 resistors on the breadboard. These are 120 ohms resistors that bridge the CAN low and the CAN high connections for both transceivers. In practice, when there are more than 2 transceivers, then only the 2 transceivers at either end of the physical bus will use the 120 ohms resistors. The nodes in between, if any, but not in this demonstration, will not require a bridge resistor. There are electrical circuit calculations that determine the value of the resistor. There is a minimum length for the physical bus. However, in this demonstration, these arrangements do not affect the flow of messages. This figure is from a Texas Instruments publication that I have referenced in the source sketch that you will see shortly. Instead of interpreting my rat's nest breadboard layout diagram, you can understand and see the simplicity of the CAN bus from this figure. In our demonstration, nodes 1 and N are the UNO and the Giga respectively. Both boards have their own CAN controllers. These CAN controllers have terminal designations CAN RX and CAN TX that connect to their respective transceivers. We use external transceivers, the SN65 HVD-230 board, as the CAN transceiver. The transceivers have CAN low and CAN high terminals that are chained together to form a service bus. Note the use of resistors at either end of the bus. The Texas Instruments Guide explains the calculation steps for the value of the resistor. I simply used the most common published value, 120 ohms, and it worked. There should be some consideration for the minimum length of the bus, but again, the breadboard seemed to have worked, and I saved myself some electrical circuit calculations. The nodes in the middle, from 2 to n-1, do not use any resistor to bridge the bus. The UNO R4 will send messages onto the CAN bus. Arduino has provided an example sketch for this purpose called canwrite.ino. I have modified this sketch to replace the output on the serial monitor with some nominal but not equivalent displays on the LED matrix. These changes are primarily to let the user know that the sketch is progressing along with the execution of the code. Connecting to an available Wi-Fi network for future extensions to exchange messages with the broker. In other words, the UNO R4 would act as a bridge between the CAN bus and a LAN infrastructure. This part in the current demonstration is limited to simply establishing a Wi-Fi connection as we have done in previous demonstrations. If you do have an interest in CAN bus applications, I would recommend that you browse the Texas Instruments reference guide on the subject. You can read about the structure of the standard CAN message in that document. The key focus in our demonstration is the data section, which can be up to 64 bits. All the other fields will be filled in by the CAN library functions for simple usage. Let me jump to the section where the message is assembled. So we have the CAN ID and we have a counter, message counter here, that we initialize globally. In terms of sending the message, we have a buffer, our 64-bit buffer, and the rest are blank initially. We use the memcopy function to stuff the current message count in the middle, that is offset by 4 bytes, and we put it in there. It's an int, so it'll go in there. And then the CAN message function, using the standard CAN ID that we've identified, assembles the payload that is written to the bus. The message count is inserted in the day buffer using the time-honored memcopy operation. Let us pray and hope that no hacker uses this code to perform a buffer overflow experiment. Ideally, we should have more boundary limit checks on the data lengths before performing these types of operations. Or in the case of desktop application development, rely on current safe C++ libraries. A CAN library function, CAN-MSG, composes the standard CAN message that is pushed out to the CAN bus. Let me back up to the setup section of the sketch. The only CAN bus related operation here is to set the bit rate for the data communications and initialize. The original Arduino example used 250K. I had to use 500K for a successful message exchange. If the function completes with no errors, then the heartbeat signal is not displayed in the LED matrix. In the loop section, we place the message count in the data buffer and write the standard message to the CAN bus. We then display the count on the LED matrix and increment it for use in the next iteration. The messages are sent every second. There is an extended CAN message buffer too that is documented in the Texas Instruments guide. Before I upload the CAN write sketch to the UNO R4, let us briefly review the sketch that will read messages on the CAN bus. This sketch will run on the Giga R1 board. This sketch too is from the Arduino example for the CAN bus. I did not make any modifications to the sketch except to align the bit rate to 500K, since this value worked well for my tests. The setup function initializes the serial connection. In keeping it simple, I retained the use of the serial monitor window output for the sketch. The bit rate is initialized. In the loop function, we check if there is a message on the bus. All messages detected on the CAN bus are read and then printed in the serial monitor window with a timestamp for our demonstration purposes. Let us upload this sketch first so that we are ready to receive all messages on the CAN bus. The compiler is still busy, and now it's uploaded, and very shortly we will get the confirmation message. Let us now go ahead and launch the CAN write program on the UNO R4. So we want to upload it by clicking on this button, and it steps through the compiling and starts the uploading. And very shortly, the uploading is complete. As you can see, it's done uploading. And now we will move over to the monitor. As you can see in the Giga monitor, we are now receiving messages, and the count is in the middle that we stash. And we've received, it's in hexadecimal, the record count. So it's down to 11. This is 12. D is 13. E is 14. And F is 16. So you get the idea that we're now cycling through the messages. The UNO writes the messages, and the Giga reads it. And you can see on the timestamp here, it's changing. And so we're getting messages almost every second owing to the delay in the network there. Okay. Once the messages are posted every second, we can view the serial monitor window of the sketch running on the Giga to see what was received by this board. And sure enough, we're receiving canned messages. It is unremarkable that not a single message is lost in this demonstration. However, one should explore how message priorities can be handled when there are 3 or more nodes on the CAN bus. So we're still receiving messages. We've received almost 47,500 messages on the CAN bus from the UNO R4 to the Giga R1 without a single error. This is a testament to the reliability of the CAN bus for messaging purposes. Now, obviously, as I said before, if you have more nodes, then the priority handling of messages comes into play, but we will not consider that for this limited demonstration. So once again, I hope you have some fun in trying to make CAN bus work for your environment, especially in trying to use the OBD-II connector from your automobile to Arduino eventually as a sketch and display the information. One of the reasons I mention this is most commercial apps limit the number of inputs that you can process at the same time, and they're generally around 4. But you may be interested in 5 or 6 or even more signals from your car to be monitored concurrently, allowing yourselves a little bit of extra room to connect using the CAN bus. You can perhaps capture more signals. This video tutorial is a quick introduction to the new features of the Arduino UNO R4 Wi-Fi board. In the interest of time and lack of meaningful projects on my part, I omitted 2 of the newer features of the UNO R4 board. These are the capacitive touch sensing unit and the mouse keyboard emulator. The sketches demonstrated in this video are from the Arduino website. I sincerely hope that you will find the new UNO R4 features that are on board very interesting for your own evaluation. As always, let us hope that there will be an UNO R5 sooner rather than later. That's all, folks. Thanks for taking the time to view this presentation. Would love to hear from you with your feedback. You're always welcome to be critical in any which way you can. Until next time, bye for now. This presentation was prepared with assistance from Arduino for the examples used in the demonstrations, and from free open source software, FOSS, for Inkscape, LibreOffice, OBS Studio, Kdenlive, and Ubuntu. Teachers, viewers, and peers provided valuable feedback. My apologies if I have inadvertently omitted anyone from this acknowledgement. A very big thank you to y'all for the assistance.